Hello friends, in this video I'm going to discuss some problems related to the concept of convergent and divergent sequences. In my previous video I have discussed the meaning of convergent and divergent sequences. In this video I'm going to discuss some problems related to this concept. Let us first recall the definition of convergent sequences. A sequence AN is said to converge to a real number L if given epsilon positive, however small it may be, there exists a positive integer m which depends on epsilon such that mod an minus L is less than epsilon for all n greater than or equal to m. This is the meaning of convergent sequence. Okay, now coming to the problems, first is by definition show that the sequence 1 by n square converges to 0. We want to show this sequence with nth term 1 by n square converges to 0 using the definition. Okay, now let us solve this. Here an is 1 by n square and limit is L is 0. Okay, now let epsilon greater than 0 be given. Okay, now mod an minus L, which is mod 1 by n square minus 0 is equal to mod 1 by n square, which is 1 by n square only. Okay, now mod an minus L is less than epsilon, that is 1 by n square is less than epsilon here, where epsilon positive is given. Now 1 by n square is less than epsilon if n square is greater than 1 by epsilon. Clear? That is, if n is greater than 1 by root epsilon, I can write like this. Okay, now we want to find this positive integer m which depends on epsilon such that mod an minus L is less than epsilon for all n greater than or equal to m. Now, if m is a positive integer greater than 1 by root epsilon, then if m is a positive integer greater than 1 by root epsilon, then we will have mod an, then we have mod an minus 0 is equal to 1 by n square minus 0 is less than epsilon for all n greater than or equal to m. We have this. Okay. Now, this will imply limit n tending to infinity an is equal to 0. That is, the sequence 1 by n square converges to 0. Clear? Hence proved. The sequence 1 by n square converges to 0. Clear? Now we consider second, the sequence 1 by 3 power n converges to 0. Now we will show this sequence 1 by 3n converges to 0. Again by using the definition. Clear? Now here an is 1 by 3 power n and L is 0. Again here we let epsilon greater than 0 be given to us. Clear? Now an minus L, that is 1 by 3 power n minus 0, is equal to 1 by power 3n mod, which is 1 by 3 power n. Now this is less than epsilon if 3 power n is greater than 1 by epsilon. Clear? Now, that is, if log 3 power n is greater than log 1 by epsilon, I can write like this. Since the logarithmic function is an increasing function. Okay, so I can take log both sides. This will imply 3 power n greater than 1 by epsilon. Since logarithmic is an increasing function, so we have log 3 power n is greater than log 1 by epsilon. This is the definition of increasing function. Okay, now this will imply that is if n log 3 is greater than log 1 by epsilon. Clear? This means that is if n log 3 is greater than log 1 epsilon, 1 by epsilon. Clear? Now, this will imply, this will give us that is if n is greater than log 1 by epsilon divided by log 3. Clear? Now, if m is a positive integer, if m is a positive integer greater than log 1 by epsilon divided by log 3, then we have an minus 0, that is 1 by 3 power n minus 0 is less than epsilon for all n greater than or equal to m, and this will imply limit n tending to infinity an is equal to 0. That is, the sequence 1 by 3 power n converges to 0. Clear? Now we consider the third problem. Show that the sequence 3n minus 1 divided by 4n plus 5 converges to 3 by 4. Again, we have to show this using the definition. Okay. Now here nth term is an is 3n minus 1 divided by 4n plus 5 and limit L is 3 by 4. Let epsilon greater than 0 be given. Now, mod an minus L, that is 3n minus 1 divided by 4n plus 5 minus 3 by 4. This is mod an minus L. Clear? Now, this is I will write again this is 3n minus 1 divided by 4n plus 5 minus 3 by 4. Okay, now this is taking LCM. This is 4 into 3n minus 1 minus 3 into 4n plus 5. And this is 12n minus 4 minus 12n minus 15 divided by 4 into 4n plus 5. Now this will get cancelled out and we are left with minus 19 in the numerator divided by 4 into 4n plus 5. Okay. Now this is minus 19 in the modulus. Therefore this is 19 divided by 4 into 4n plus 5. I can write like this. Okay. Now this is clearly less than 19 by 4n plus 5, since here we have denominator is more here less. Therefore we have this is again less than 19 divided by 4n. Since 4n plus 5 is more than 4n, again I can write like this is less than 19 by n. Since here 4n and 4n is more than n, so we have again this, and this is less than epsilon if 19 by n is less than epsilon if n by 19 is greater than 1 by epsilon. Clear? That is if n is greater than 19 by epsilon. I can write like this. Clear? Now, if m is a positive integer, m is a positive integer greater than 19 by epsilon, this, then we have an minus 3 by 4, that is 3n minus 1 divided by 4n plus 5 minus 3 by 4 is less than epsilon for all n greater than or equal to m. So we have this, and this will imply limit n tending to infinity an is equal to 3 by 4. That is the sequence with nth term, this 3n minus 1 divided by 4n plus 5 converges to 3 by 4. Converges to 3 by 4. Clear? Okay, clear? Now we will discuss some problems related to divergent sequences. For this, let us first recall the meaning of diverges. Okay, first is a sequence an is said to diverge to plus infinity if given any positive real number k. However large, there exists a positive integer m which depends on k such that an is greater than k for all n greater than or equal to m. Then in that case we write limit n tending to infinity an is equal to infinity. This is the meaning of a sequence diverges to plus infinity. Same way we have a sequence an is said to diverge to minus infinity if given any positive real number k, however large, there exists a positive integer m depending on k such that an is less than minus k for all n greater than or equal to m. And in this case we write limit n tending to infinity an is equal to minus infinity. This is a sequence that is said to diverge to plus infinity. We have this an is greater than k for all n greater than or equal to m, and this m depends on k, and a sequence diverges to minus infinity if we have an is less than minus k for all n greater than or equal to m. Okay, now we come to some problems. Okay, now again using the definition, show that by definition show that the sequence 2 power n diverges to infinity. Okay, let an is equal to 2 power n and let k greater than 0 be given. Okay, now an is greater than k. This will imply 2 to the power n greater than k. Okay, now taking log both sides, since a logarithmic function is an increasing function, we have discussed earlier also. So this will imply n log 2 is greater than log k. This implies n is greater than log k divided by log 2. Okay, since log 2 is positive. Now, if m is a positive integer, m is a positive integer greater than log k divided by log 2, this one, then we have an is greater than k for all n greater than or equal to m, and this by definition will imply limit n tending to infinity an is equal to infinity. That is the sequence 2 to the power n diverges to infinity. Hence proved. Okay, now clear. Now we consider second problem. Show that the sequence log 1 by n. Show that the sequence log 1 power n diverges to minus infinity. Again by using the definition. Clear? Log 1 by n. Now let an is equal to log 1 by n and let k greater than 0 be given. Okay, now an is less than minus k implies log 1 by n is less than minus k, and this will imply log 1 minus log n is less than minus k, that is minus log n is less than minus k, log 1 is 0. Okay, and this will imply log n is greater than k. Clear? And this will give us n is greater than e to the power k. Clear? Now if m is a positive integer greater than e to the power k, then we have an is less than minus k for all n greater than or equal to m, and this will imply by definition limit n tending to infinity an is equal to minus infinity, that is the sequence log 1 by n diverges to minus infinity. Clear? Okay, clear? This is the sequence log 1 by n diverges to minus infinity. Clear? Now we consider next problem. Show that limit n tending to infinity x power n is equal to 0 where mod x is less than 1. Okay, this is very important problem. Limit x power n where n tending to infinity is 0 where mod x is less than 1. Okay, now let us solve this problem. Solution. It is given that mod x is less than 1. It is given. So there exists some h positive such that mod x is equal to 1 upon 1 plus h, since h is given to be positive. Mod x is less than 1. It is given. So we have some h positive such that we can write mod x is equal to 1 upon 1 plus h. Okay, h is positive, so 1 plus h is more than 1. Therefore, 1 by 1 plus h is less than 1. Okay, clear? And this will imply mod x power n is equal to 1 by 1 plus h power n. Okay, mark this as 1. Now, using binomial theorem, 1 plus h power n is equal to 1 plus nh nc1 nc2 h square up to ncn h power n, and this is equal to 1 plus nh plus n into n minus 1 divided by 2 h square up to h power n. Okay, and this will imply 1 plus h power n is greater than or equal to 1 plus nh. I can write like this. For all n positive, since h is positive, from this we get this. Clear? Now this will imply 1 upon 1 plus h power n is less than or equal to 1 by 1 plus nh for all n. Okay, mark this as 2. Okay, now from 1 and from 2 we get, from 1 and 2 we get mod x power n, which is 1 upon 1 plus h power n is less than or equal to 1 by 1 plus nh. Okay, for all n. Now let epsilon greater than 0 be any real number. Then we have mod xn minus 0, which is mod xn is less than or equal to 1 by 1 plus nh is less than epsilon if 1 plus nh is greater than 1 by epsilon. That is, if nh is greater than 1 by epsilon minus 1, or I can also write this 1 by h here. We have this. Okay, I can write like this. Now let m be a positive integer greater than 1 by h into 1 by epsilon minus 1. Then we have xn minus 0 is less than epsilon for all n greater than or equal to m, and this will imply limit n tending to infinity xn is equal to 0 provided mod x is less than 1. Clear? Hence proved. Okay, clear. Now we consider next problem. Show that if x is greater than 1, here we have taken mod x is less than 1. Now if x is greater than 1, then limit n tending to infinity xn is equal to plus infinity. Okay, now if mod x is less than 1, then limit n tending to infinity xn is 0. But if x is greater than 1, then limit n tending to infinity xn is plus infinity. Again, this is very, very important problem. Okay, now let us now solve this. Okay, here we have x is greater than 1. So we can take x to be 1 plus h for h positive. For some h positive, h is positive, 1 plus h will be more than 1, and it is given to us x is greater than 1. So I can take my x to be 1 plus h for some h positive. Clear? Now, therefore, x power n is equal to 1 plus h power n. Okay, now again using the binomial theorem, this is 1 plus nc1, that is n, plus nc2, that is n into n minus 1 by 2 h square up to h power n. Okay, clear? Now this is equal to, this implies x to the power n is greater than 1 plus nh for all n since h is positive. I can write like this, mark this as 1. Okay, now let k greater than 0 be any number, then 1 plus nh is greater than k if nh is greater than k minus 1, or I can shift this h here to the right hand side, that is if n is greater than k minus 1 divided by n. Now let divided by h, sorry. Let m be a positive integer greater than 1 by h into k minus 1. Then x to the power n is greater than 1 plus nh here, which is greater than k. X to the power n is greater than 1 plus nh, which is greater than k for all n greater than or equal to m using 1, and this will imply limit n tending to infinity x to the power n is equal to plus infinity. Clear? Okay, clear? Now next problem, we consider next problem. Show that the sequence minus 1 power n does not converge. Does not converge. The sequence minus 1 1 minus 1 1 does not converge. Okay. Now we have sequence an is minus 1 power n, which is minus 1 1 minus 1 1 and so on. Okay, this is our sequence, given sequence. Now we have to show this sequence does not converge. Okay, now let if possible limit n tending to infinity an is equal to l. Then for epsilon is equal to 1 by 2, there exists a positive integer m such that mod an minus l is less than 1 by 2 for all n greater than or equal to m by definition. Okay, mark this as 1. Now 1 will imply 1 minus L mod 1 minus L is less than 1 by 2 for all n greater than or equal to m and n is even. If n is even. Since sequence is defined like this, minus 1 1 minus 1 1. Now an is 1 if n is even. Okay. And minus 1 minus L mod minus 1 minus L is less than 1 by 2 for all n greater than or equal to m and n is odd. Okay, now this is mod 1 plus L is less than 1 by 2 for all n greater than or equal to m and n is odd. Clear? Now this is when n is even, this is when n is odd. Clear? Now 2 is equal to 1 minus 1 plus L plus 1 minus L. L will get cancelled out. 2 can be written like this. Now using triangle inequality, mod x plus y is less than or equal to mod x plus mod y. This is mod 1 plus L plus mod 1 minus L. Clear? Now this is strictly less than from here. This is 1 plus L is strictly less than 1 by 2 mod 1 plus L from here, and mod 1 minus L is strictly less than 1 by 2. So we have this, which is 1 means we are getting 2 is strictly less than 1. It is a contradiction. We are getting what? 2 is less than strictly less than 1, which is a contradiction. Therefore, we arrived at a contradiction. Therefore, our assumption was wrong. Okay, therefore, our assumption is wrong. Our assumption is wrong. And hence, or therefore, sequence minus 1 power n is not convergent or does not converge. Is not convergent or does not converge. Clear? Okay, clear? Now that's it for this video. If you have any queries or any suggestions, please write to me in comment box. Thank you.